first is to change your weight update based on, to mitigate these effects. So the example that we'll talk about is an algorithm called MERA, which is margin-infused relax algorithm. And what this is in the perceptron algorithm, we're just choosing a weight update that's equal to F, and what MERA is saying is, how can we adaptively change this weight update in a more intelligent way? And so the key idea here is to, instead of updating the weight with your feature vector F, is to update it with some multiple of F. And the multiple of F that it chooses is the F such that the weight vector is changed such that the current example is fixed. And the next weight vector will correctly classify and get this instance right. So if you have your weight vector and F is the correct label of F is actually Y star, then instead of adding exactly F, in the case of the perceptron, why not add something smaller than F or something bigger than F? So the goal is to fix the current mistake, but also minimize the change to W. And you can write this down as an optimization problem. And what that would look like is you want to pick the weight update. So we're only looking at a single weight update. And you can pick the weight update that minimizes the difference between the old weight vector and the new weight vector, such that your current example, the correct label, the correct activation is more than the incorrect activation. And we're also at a +1 so that we say that it's not just greater than or equal to the current weight vector, but it's greater than the current activation by at least 1. And this +1 helps you generalize, and so that you're not actually just barely fitting the data, but you're also having a bit of a margin. And also, if you didn't have this +1, then you could just set them all to be equal and set all the weights to be 0, and this would be satisfied. So the goal is to solve this optimization problem for every single update that you do with the MERA algorithm and find the update. So you want to find the value of tau that minimizes the change and also satisfies this constraint. So what this looks like is you have your weight update right here, and here's your optimization problem. And the current weight vector minus the old weight vector doesn't necessarily have to be in the direction of F, but it turns out that that is actually the direction of the update that will minimize this, because if it's in a different direction, then that vector is actually going to have it will have some non-zero component that's not in the direction of F. And then this equality, this right here the weight vector will have some component that you're adding to it that doesn't relate to and doesn't mean anything in this inequality. So you can rewrite this as minimizing tau times F, which is the difference between your current and previous weight vector, and subject to your original constraint. And so in this case, F is fixed. You can't choose what F is, and you can only choose what your weight vector is. So you want to choose the tau such that you want to minimize tau squared such that this inequality holds. And so tau squared is a function that looks like this. If you didn't have this constraint right here and only looked at the first part, then you would always just pick tau to be 0. But you have this constraint, and what this constraint looks like is you'll have a line right here that is the case in which your old prediction is equal to what the correct prediction plus 1. And so to solve this, you want to find the minimum value of tau that satisfies this inequality, which will be exactly at the point right here. So to solve this, you just need to solve a system of equations between these two functions, and it comes out to be this right here. So we can look at this and say, well, it kind of makes sense because the your tau is going to be bigger based on the difference in the classified before and classified after. Any questions on that? Okay, so you compute your tau at each time step and then update your weight vector based on this tau. And you update it according to this rule right here. Yes?
So what does the denominator of the tau expression say is being covered in the actual slide?
Oh, sorry. The denominator is 2 times f dotted with f. So, I don't know if I can, there we go, like that. Okay, so in practice, sometimes you might have updates that are very, very large in the case of having noise in your data. So if you have one example that is very incorrectly classified, then you're going to have this huge update. And it's not good to make these huge updates because one, that data point might be incorrectly labeled, it might be noise, and also, in general, it'll converge faster if you make smaller updates. So what you can do in this case is take your update before, which is written right here, and cap it, and set a limit to how big of an update you're going to set. And that limit will be defined by C. And geometrically, what this looks like is you'll have the update will minimize tau in some range right here. Or it'll have tau be in this range right here. And usually when you use this update instead, it converges faster. And I mean, you might say why, like, I don't know, this looks a little complicated. Why do this? And it actually turns out that you can derive this you can derive that this is the best thing to do. Theoretically, by looking at the case in which you have noisy data and want to minimize the number of errors that you have, subject to the fact that you might have some noise in your data. Yes?
Well, I guess so this is probably the wrong way of thinking, but I would feel like it would be worse on noisy data because you would be trying to like fit it to the outliers instead of just like accepting the more mistakes.
So that's exactly what the C is for. So if it does see an outlier, then the maximum update, it won't update to the case in which that noise is correctly labeled. It'll only update the weight vector by C.